This is the first lecture of PMATH 451. Before we go into the general theory of measure and integration on general spaces, let us start by giving a brief review of the Riemann integration and also give a little bit of motivation on why we do this integration using the measure theory. So if you recall, the idea of the Riemann integral is that if you have some function, let's say here's x and y, and you have a function f of x, and you want to find the area of this function between a and b. So the idea of Riemann is that let's do a partition of this AB. So let's divide AB into some small pieces. So let's call this x0 less than x1 less than the last one, let's call it xn. And then on each of these pieces, the Riemann integral is saying you can use a rectangular area to approximate the total area of this function. So you use some rectangular area like this. So in other words, on each of these subinterval, you pick some sample points, let's say S1 up to Sn. So the area of each of these rectangle is given by the function evaluate at the sample points Si. And then you multiply the width of this rectangle, which is xi minus 1. And that's give you the area of the ith rectangular region. And now you sum them up. So I going from 1 to n. Then hopefully, if your function is nice enough, it behaves good enough, then this finite sum will converge when you start chopping this interval AB into smaller and smaller pieces. So when these actually n goes to infinity and also these intervals are going to be small, they will converge to some number, and you call this number the Riemann integral of this function. Kind of give you a measure of how the area of this function under the area under this function, basically. All right, so that's the idea of Riemann. So let's talk about, I don't want to get into the detail of Riemann integral. You can go back to your first year calculus course and review. I do want to get into the limitations of Riemann integral. So this course, in this lecture, we're talking about its limitations of the Riemann integral. And I would like to say there are probably 3 limitations I want to bring to your attention. So first of all, the first limitation is it heavily relies on the structure of the real line. So as you can see in the definition, you are requiring to have a partition of the interval. And suppose you have some function f on some general space, let's say just x to, let's say, real value functions. And this x can be some metric space or just a set. Okay, there can be some metric space. For example, it can be the set of rationals, it can be Rn, it can be really any set. For example, the set of A, B, and C, and so on. So it can be anything. And we want to make sense of an integration for such function. And it's very difficult if this set X is not equals to R. And probably in your second year calculus, you learn how to do integrations on Rn. But if you think about it, if you take a function on the rationals, for example, there's not a good way of defining Riemann integral. So the Riemann integral is really limited on this structure of the real line. And the second is that there are not many functions are Riemann integrable. So let's say not many functions are Riemann integrable. And why do I say that? Well, here is a theorem that I want to bring to your attention. We're not going to prove this theorem. It's a theorem due to Lebesgue. I think I misspelled his name. Lebesgue. It tells you the following. So if you're given a function f from a, b to r, well, this function is Riemann integrable. That's if and only if this function is somewhat almost continuous. What do I mean by almost continuous? It means the set of discontinuities of f So the set of discontinuity of f is basically all the x where this function is not continuous. So this set is Lebesgue measure 0, or you say it's a Lebesgue null set. Well, if you recall from your 450, Lebesgue null set, in other words, there exists some intervals, let's say an, bn, so that the set of discontinuities is contained in the union of these an and bn, and you can make this an, bn to be arbitrarily small. So this is summation of this bn minus an. The length of these intervals can be less than epsilon for every epsilon. So for every epsilon greater than 0. So that's the definition of Lebesgue null set. Or you can say this has Lebesgue measure 0. So let's take an example. Suppose I just consider this function f of x. What it does is the following. So it takes an x from 0 and 1, and it will return the value 1 if x is a rational number, and it will return 0 if x is irrational. Well, so let's see, is this function Riemann integrable? Well, based on the theorem, we just need to know where is this function discontinuous. Well, if you recall from your first year calculus, this function is nowhere continuous. That's probably the first example where you have a function that's nowhere continuous. So the set of discontinuity is basically the entire interval 0 and 1. And 0, 1 has Lebesgue measure 1, it's just the length of the interval. It's certainly not a Lebesgue null set. So f is not Riemann integrable. Well, so you have a function that's not Riemann integrable. But if you really look at this function looks like 0 almost everywhere. As you can see, it's only non-zero when it's on the rationals, and the rationals are countable, while the interval 0, 1 is uncountable. So this function is really mostly 0, but only 1 on the countably many points. So you would like to say it's almost 0. You want to give a definition of an integral where the integration is 0, but you cannot do that if you're using the Riemann integral. And lastly, let's talk about the third one. What's the problem with Riemann integral is that it's not well behaved under limits. So not well behaved under limits. So what do I mean by not well behaved under limits? Let's just take f to be the same function as in the previous example. So then let's do the following. So let's let the r case, k going from 1 to infinity, be all the irrationals inside the interval 0, 1. And I would like to define functions fn of x to be the following. It will return a value of 1 if x is one of the first n r's. So it is one of the r1 up to rn, and it's 0 otherwise. All right, so let's see. So each of these fn of x is Riemann integrable because it's only discontinuous on these r1 up to rn. There's only finitely many of them, and it certainly has Lebesgue measure 0. So fn is Riemann integrable. But let's look at what's their limit. So if I take the limit as n goes to infinity and I feed an fn of x, okay, by the way, I define this fn is really a function on 0, 1. So let's look at what this limit will do, all right? So there are two cases. Well, first of all, if x is a rational, and also, of course, x has to be in the 0, 1. So if it's a rational, then it has to be one of these Rn's, because the Rn's are all the rationals in 0, 1. Then eventually the x will be one of the Rn's, and from that point on, all the fn of x will be equals to 1. So, and you can convince yourself this limit will goes to 1. And on the other hand, if x is not a rational, so it's not a rational point, then if you think about each of these fn of x will always be 0 because x is not rational. It's never one of those r1 to rn, so it's always 0. So the limit will also goes to 0. And as you can see, this limit function is exactly the function f of x we just defined, which is takes value 1 on the rationals and takes value 0 on the irrationals. And as you can see, now we have a problem. So each of these fn is Riemann integrable, but this limit is not Riemann integrable. So we have a situation where the convergence of a bunch of functions, each of these functions is Riemann integrable, but the limit, or as you can see, this is what we call the pointwise limit, is not Riemann integrable. Well, if you recall what you did in the first year, second year calculus, you introduced this notion of uniform convergence for functions that allows you to say the uniform limit of Riemann integrable functions is, again, Riemann integrable. But we sometimes still like to do pointwise limit, and Riemann integration doesn't really do anything if you only have a pointwise convergence instead of a uniform convergence. So these are the three limitations of the Riemann integral.